Hello and welcome to this video. In this video we are going to look at nuclear fusion. So we've looked at fission in quite some detail now. We know the general description of how it happens, and we know that this is one of the two ways that we can use nuclear energy in order to generate electricity. So the second way that we can generate energy from our nuclear interactions is by fusion. We introduced this briefly as just combining nuclei. Okay, so if I were to want to take two nuclei and combine them so that I have just one nucleus, I would have to undergo a fusion interaction. Now, the way this works is usually that smaller elements or smaller atoms or isotopes will be much easier to fuse together, because they will then be able to, as long as I can get over the electromagnetic force into the strong force region, I have a new nucleus. So we always use small nuclei. So what I'm going to say for this case is, what if I just have a proton and a proton? What is this going to form? Well, a proton and a proton are both positively charged, right? So this is my first proton with a positive charge. This is my second proton with a positive charge. If I want to push these together, they are going to naturally repel the other way because they are positively charged, meaning that I have to put in enough energy to overcome the electrostatic repulsion. So the whole idea of fusion is enough energy must be input to overcome the electrostatic repulsion or electromagnetic repulsion. Either one is fine. Now, in order to do this, I need to heat up the system. If I heat up the system that this is in, I'm going to end up with just a by heating up the system, we know from thermodynamics, I'm going to increase the kinetic energy of everything. If I increase the kinetic energy, I can therefore end up having enough energy so that these two will fuse together, and I will end up with just a nucleus that is just purely consistent of these two protons. Now, then that basically is a helium nucleus, right? Because I've started here, a single proton is just a hydrogen, so H11. So I've got two hydrogen nuclei. If I then combine them, I now have two protons and 0 neutrons. Now, it's because of this fact that I have 0 here. Helium in this case is not a stable isotope because I don't have the neutrons to supply to make this as stable as possible. For this reason, this small nuclei tends to be made up of isotopes of hydrogen, like deuterium and tritium. So what is deuterium and what is tritium? Well, deuterium, from this du here, means 2, right? So this is hydrogen. It's hydrogen, so it still has to have one proton, because the proton is what defines what the element is, but it now has one proton and one neutron. So it has a mass number of 2, whereas tritium, this tri meaning 3, I have still got hydrogen 1 because it's just an isotope of hydrogen, but now I have one hydrogen molecule or one proton, and I have 2 neutrons, meaning I have a mass number of 3. In that case, if I were to change this equation here into 2 deuterium isotopes, I end up with a helium 2,4, and this is the stable version. So most of the time when we're working with fusion, our fuel source is going to be deuterium or tritium. However, in a fusion reaction, I can go even further than this, and I can take maybe 2 helium sources, and I could say, what if I have helium 2,4 and another helium 2,4, and I heat up the system enough so that they have high enough energy that they can come together, and when they come together, I end up with 4 protons and a mass number of 8. Now, for those of you who are familiar with the periodic table will know this is beryllium. Okay, I've kind of skipped out lithium here because I could have also had this helium 2,4 and hydrogen 1,1, and I would have ended up with lithium with 3 protons and 5, a mass number of 5. So what you can tell from here is I can combine any nuclei together in order to create a different element. So any combination of nuclei can create a new element. And this is exactly what happens in stars. So stars are essentially just massive fusion reactions. The main fuel being hydrogen. Since hydrogen gas is the most abundant gas in the universe, the stars just have this field of hydrogen gas, and because they're so hot, they've heated up the system of hydrogen so that it has enough energy to become a plasma. And the plasma we can think of as just the nuclei, and the electrons are separated. So it's just kind of a cloud of free charges, free nucleons. So it's just kind of a cloud of, and because this is nuclear physics, we're only really worried about the nucleus. It's just a cloud of nuclei. Okay, so we've kind of separated, we've put so much energy in that we've ionized all of the electrons from this system. We end up with just a cloud of nuclei floating around. And it is therefore in stars that we actually make most of the elements that we're familiar with on the periodic table. They will create all of these elements, and as soon as a star dies, it will supernova if it's large enough, and then it basically pushes out this massive cloud of gas that are all of the other elements, and these gases will come together and they will form planets or asteroids or any of these kinds of celestial bodies that then allow us to be formed. All of the atoms in your body were originally formed in the heart of a star. So when people say that you're made out of stardust, this is what they're referring to there. This idea that stars create all of the atoms that are present in your body today. Now, what we said in the previous video is that this fusion reaction is actually going to give us out energy in the same way that the fission reactions give out energy. And this happens because of a similar sort of thing. We have a mass defect, right? If I were to look at all 4 of these equations, right, all 4 of these, if I take any of them, the mass to begin with and the mass to end with will be different, right? I'm going to end up with some sort of mass defect in the difference between these masses. Now, because of that, I will end up having some amount of energy being released because there is a mass defect in any fusion reaction. So fusion reactions will also have a mass defect, which we call delta M, which is just the difference in the mass between the starting point and your ending point, and therefore we have an amount of energy being given out, which is your mass defect, delta M, times c squared. And this is again equivalent to the amount of energy given out based on the binding energy, right? So we've changed the binding energy. After this, a helium nucleus or a beryllium nucleus or a lithium or whatever we're creating is going to have a different amount of energy needed in order to pull all of these things together. Because of that difference in energy, you've had some energy transfer and some energy is being released. Now, a different way that you can think about this, if that's not really clicking, is that if you treat these as just nuclei, they are simply just electrostatic charges, right? They are just a point charge. So let's think about this in the process of electric fields for a second. Now let's say with electric fields, let's say I have 2 point masses. These are my nuclei. So I have a positive point mass here with a charge of plus Q, and then I have another positive point mass here of charge plus Q, and they have a distance between them, let's just call it R. Okay, now in terms of energy that's currently being held, we know that the electric potential energy can be written as 1 over 4 pi epsilon naught Q1, which is just Q in this case, times Q2, which is also Q in this case, divided by R squared. Now, what this means is, since the charge of these isn't going to change as they move about, the energy is, sorry, this shouldn't be squared, just R. The energy is therefore proportional to 1 over R, meaning the closer they get, the larger the potential energy becomes. Because I'm getting smaller and smaller and smaller, I have more and more energy being held in this system. So as the nuclei come closer, their potential energy increases. Okay. However, as soon as they cross that threshold and they become a single point charge, that single point charge then has no potential energy anymore, which means all of this potential energy is then lost instantaneously. And because we can't lose it, the potential energy then gets kind of pushed out as the energy given out in a fusion reaction. So the potential energy falls to 0 when they combine, or when they fuse, should be a better word to use, when fusion occurs. And when fusion occurs, this then leads to this idea that this change in potential energy is the energy, putting equals here, is the energy given out. Okay, so this is another way that you can think about how energy is actually being given out in this relationship, because if I just had one point charge of plus 2q, its energy then is going to be different to the energy that it had when it was two separate q's and they were getting closer together. But this is very rarely going to come up. Most of the time they will just talk about this idea that you can have some sort of mass defect when a fusion reaction occurs, and then you can calculate the energy transferred by looking at E is equal to delta mc squared. Now, there are issues with fusion. Okay, so fusion reactions are useful. They give out quite a lot of energy. In fact, a fusion reaction gives out almost 10 times as much energy as a fission reaction. So we said that fission reactions, I'll put this down here, give us something on the order of 0.5 mega electron volts. Actually, fusion reactions, for each reaction that occurs, we're looking more on the order of 5 electron volts, which is times 10 more. Now, if we've got a method here of getting 10 times the amount of energy, and we're using hydrogen, which is a very abundant gas, why are we not doing this all the time? Surely if we have this kind of method we know that works, why are we not trying to utilize this and get as much as possible? So now we have to look at the issues with this. So the issues of fusion. Now the biggest one, and probably the main one that will ever come up, is the fact that we have to input energy in order to overcome the electrostatic repulsion. And what we find is that the energy used to overcome the repulsion is actually greater than the energy given out by the fusion reaction, because we can't have a 100% transfer of this energy to overcome the repulsion, because we do this by the thermal energy, so we heat, but also we have a high temperature and we have a high pressure also, in order to cause this plasma to occur. Now, in order to make a high temperature, that requires a lot of thermal energy to make that happen, and to have a high pressure, that requires a lot of work done to be transferred to the system in order to actually change its volume, therefore changing its pressure. So it means that if the energy that we're trying to get out, we have to put in even more energy to try and get it to occur in the first place, then it's not really worth it in the end. So it's not economical. It's not economical to carry out fusion. Now, saying that, it is kind of a goal that one day we will be able to carry out fusion on a regular scale, because we'll figure out a more efficient way to transfer this energy, or we'll figure out a more efficient way to try and get particles or nuclei to fuse together, releasing the exact same amount of energy. There was a single experiment, which is kind of a one-off, which was cold fusion. And this was a single experiment that claimed to have observed fusion. So it claimed to observe fusion at room temperature. And if this is true, this must mean that we could actually carry out fusion all the time, because every room is room temperature, right? So this means that we could do this all the time. But this was a single experiment that was never able to be repeated. Okay, it could not, it's not repeatable. And we know in the science community, if we can't repeat the results of an experiment, that must mean that something happened in this experiment to cause them to have inaccurate results, right? Because the laws of physics don't change depending on the time that things happened, right? It's the laws of physics are the laws of physics. If this thing is not repeatable during the same thing, it must mean that either something in their experiment went wrong and they read an incorrect positive result, or they just lied because they would get money out of that. Now, nobody really knows what happened, but it is common for them in exam questions to kind of ask you about this cold fusion as a way to get 1 or 2 marks, to ask about why is this an example of why the scientific community needs to repeat experiments or something like this. So this is now going to wrap up fusion. So we know that fusion is just going to be the collision, or the very high velocity collision of nuclei to overcome those electrostatic repulsion, then leading into the strong nuclear force range. We know that any combination of nuclei creates a new element because we've changed the number of protons. This happens in stars. We know that we can calculate the amount of energy that's been produced by the mass defect in between the thing that we started with and the end product, and we state that fusion actually produces 10 times the amount of energy as fission. We thought about it in terms of the electric field energy, and now we know that the issue that we have, the reason that we can't carry this out on a day-to-day basis, is because the energy that we're putting in to overcome the repulsion is actually bigger than the energy that we get out from the fusion reaction. Therefore, it's not economical to actually perform this in everyday life. Thank you for watching.